Hey, Chem 20s, how you doing? It's Mr. Jukley here. We are going to get going on a lesson for this week, this holiday Monday week that we've got here. Holiday Friday too, but Monday is the one that we've got off that we're supposed to have our class. We are going to do something a little bit different. So we are going to be talking about this concentration piece and how to calculate concentrations. But we are going to kind of skip little parts. We're going to focus on the essentials for the next level. So we're going to skip part of it, but we're also going to have a little bit of a mathy review before we get into the actual calculations. So things that you will need for this particular lesson. Oh, and it's a bit of a longer one as well. So we're going to actually break it apart into probably two. We'll do the mathy review as one sort of mini lesson, and then we'll do the calculations as another lesson. So you can think of it as one bigger lesson or sort of 1.5 lessons or something like that. I don't know, but that's what we're working on for this holiday Monday week. So again, things that you will need for this. The usual, you'll want your workbook and your data book and a pencil or something to write with. So the usual means of that. But you'll probably also want just like a scrap piece of paper for the review section because it's not actually in our notes. And then, and obviously a calculator if we're doing mathy stuff. So please, if you don't already have all those things ready, put the video on pause, go grab them. Once again, data booklet, work booklet, scrap paper, calculator, and something to write with. So put the video on pause now and grab all of those things. Alrighty, so we've got everything we need. We'll probably start on the scrap piece of paper with our little bit of math review. So I've got a title here, Chem 20, a bit of mathy review. Let's go through and let's have a look. The first thing I think we might want to talk about is unit conversions. And we'll just do some of the common ones that we see in Chem. So we often see things like milliliters, and in Chem we want to change those to liters. So when we're looking at this, these are units, and we need to know what those actually mean and what they actually say to us. So capital L for liters, lowercase m, capital L for milliliters. So these are two very, very, very common ones that we look at. And the conversion factor that we see for this is there are 1,000 milliliters in 1 liter. So in other words, those are the exact same thing. 1,000 milliliters is equal to 1 liter. We also sometimes see kiloliters, and in chemistry, we typically want to put that into liters. So the conversion factor that we've got for this, we've got 1,000 liters, is equal to 1 kiloliter. And we need to know what goes, the 1,000 goes with in this part, the liters, and the 1 goes with the kiloliters. So those are probably our most common ones for that. Other ones that we've got, other ones that we can go through and talk about here. Let's see. Milligrams into grams, and grams is going to be our standard unit for chemistry, and that's actually what I'm doing for all of this. This is our usual, I did something wrong there. Usual, there we go, chem units is what we're putting on the left-hand side, and I'll circle them all afterwards. So milligrams to grams, just like milliliters, well, there's milli is 10 to the negative 3 or 1,000 depending on how you look at it. So messing up like crazy already here. So that's 1,000 milligrams is equal to 1 gram is our conversion factor. Cool, perfect. Let's see, another very common one is kilograms, and we need to be able to turn that in grams. If you're taking physics at the exact same time, this is kind of annoying because in physics we always use kilograms, but in chemistry we always use grams. There are 1,000 grams in 1 kilogram. Perfect. What are some other ones that we'll look at here? Let's look at moles. So oftentimes we see millimoles, and we'll want to turn that into regular plain old moles that we use in chemistry. There are 1,000 millimoles in 1 mole. Perfect. So I'm pretty sure those are our biggest conversion factors that we're going to need to be able to deal with here. So honestly, there's a ton of different ways that you could look at this. I would probably go through and either or um, memorize or use a little bit of common sense with this as well, right? And if we think about milliliters to liters, that's a good one to use for common sense. So you've got a juice box. Here's a juice box, there's a little straw, and we know that juice boxes, I think at least, juice boxes are 250 milliliters. So a juice box might be that big, it's 250 milliliters. Then we go and we can get like the bigger juice boxes, the ones that are meant to be shared and they don't have a straw. They have that little like flip top thingy up there. And we know that those ones are 1 liter. So a big juice box versus a small juice box. So we know that we could fit more of these small juice boxes into one of these. So as I'm going through and I'm trying to convert 250 milliliters into liters, all of these ones, what we have, oh, that's left over from yesterday, all of these ones, we're either going to multiply by our conversion factor or divide by our conversion factor. So multiply by 1,000 or divide by 1,000. And if we use a little bit of common sense, things make a lot of sense. So if I wanted to look at what 250 milliliters are, and I want to change that into liters, I could go through and I could just kind of guess, and I could say, oh, well, I know the conversion factor is 1,000, so I'm going to multiply by 1,000, and that's equal to 250,000 liters. Now let's just think about that for a split second. If a juice box is 250 milliliters and it is this big, I'm going to highlight it in red over here. The juice box is this big. Does that mean that it's going to make 250,000 of these 1 liter boxes? That doesn't make any sense. One of these 250 milliliter boxes does not equal 250,000 of the bigger boxes. So we know that this is wrong, right? A little bit of common sense goes a long ways. So then I go through and I say, okay, 250 milliliters, let's try dividing it by 1,000. So 250 divided by 1,000 is 0.250 liters, and that makes sense, right? Because 0.250 liters is less than a liter, and this 250 milliliter juice box is less than 1 liter. So again, common sense goes a long ways here. Now that being said, does go a long way, but there are better ways to look at this. We're kind of looking at 1,000 is our conversion factor for just about everything. If you ever do end up taking physics, you need to know a ton of other conversion factors, and honestly, it's just handy to know for your everyday life. So again, I'll just kind of mention this. These are our normal chem units, and you need to know how to get from some of these funky units on the left-hand side over to our standard, our usual, regular, plain old chem units on the right-hand side. So again, one way is kind of looking at common sense. Another way that we could look at this, and let's just keep using this same example here, is we could go through and we could look at conversion factors. And this is actually the part that we'll spend a lot of time on the next little while. A big part of chem is based on conversion factors. So let's start with that 250 milliliter juice box, right? That same one, the one that's highlighted in red up there. We know that it's 0.250 liters. It's kind of a bit of common sense. We figured it out that way. But we want to use conversion factors. So what a conversion factor is essentially a fraction, so a numerator and a denominator, where we are focusing on the units. We are canceling out units that we don't want, and we're ending up with units that we do want. So the units have to be in kind of opposite spots. So we know that we've got numerator and denominator. So things in the numerator will cancel with things in the denominator. And we can think about that in terms of like numbers. Like what's 5 divided by 5? So 5 in a numerator divided by 5 in a denominator. The 5's cancel out and we're left with just 1. Doesn't matter if it's 5 divided by 5 or a million divided by a million. They're always going to cancel out. Cool. So what I need then is to just think about this. Does 250 have a numerator and denominator, this 250 milliliters that I've got right here? It does. It's just we don't often show that denominator. So if it helps, you can put the denominator on the bottom. 250 divided by 1 is still just 250, right? And you don't necessarily need to put that on the bottom, but you can if you want. So the next piece that we're looking at is we're looking at this second fraction over here. We need to multiply by a second fraction, and we want to cancel out milliliters. So before I even think about the numbers, I currently have milliliters in the denominator, or sorry, in the numerator. Definitely milliliters in the numerator. If I want to cancel it out, I'm going to put milliliters in the denominator. So opposite spots. One's on the top, the other's on the bottom. Those are going to cancel out. The thing I want to end up with, I'm going to leave on the top. So liters in this case, I want to end up with liters. I'm going to put liters on the top. And then I just need to think to myself, well, how many milliliters in 1 liter? There are 1,000 milliliters in 1 liter. So things that we notice here as we go through, and let's cancel out those milliliters. Let's get rid of them. Things on the top cancel with things on the bottom. That is the entire key. So let's go through and let's check this out. Let's get out our calculators. Come on, calculator. There we go. Of course, it doesn't want to turn on. There we go. So if I were to plug this in, I'd say I've got 250. So that's on the top. Divided by 1. Do we really need to divide by 1? So do I need to hit divide by 1 in my calculator? Not so much. We could do it, and then we'll do it with and without and see. Then I'm going to be multiplying by 1. So everything on the top we multiply. So times 1 still doesn't change anything. And then divided by 1,000. So that's going to give me 0.25. 0.25, and if we're looking at sig digs, which we'll talk about in a second, should be 0.250 liters, which is exactly the same thing that we looked at before. Now let's just try that. Let's say we forgot about the ones here. So 250, plugging this into the calculator here, divided by 1,000. Oops, that's an extra 0. Delete that 0, and we end up with 0.250 liters again. Right? So it doesn't matter. So I'm looking at the calculator over here. It doesn't really matter if I include the ones or if I don't, as long as things on the top we multiply and things on the bottom we divide. So let's just make a little summary of this. So focus on units. Focus on units first, and we're trying to cancel out those units. All right, so units on top can cancel, running out of space, just barely got it, with units on bottom. Excellent. So units on the top can cancel with units on the bottom. And then we plug the numbers in after. Put numbers with right units. Right is not a direction. Correct units is what we're talking about here. And then finally, when we're actually calculating, if it's on the top, we multiply. Top. Let me rewrite that. Let me just rewrite that a little bit there. On top means multiply. On bottom means divide. That makes a little bit more sense than what I was originally going to write. Cool, so that's not so bad. That's not so bad. Let's maybe try one more. And I'm going to get you to put the video on pause and try it out for yourself. If you're in Physics 20 and you've already done a billion of these, which I know there's a handful of us who are doing both courses, you're probably pretty good with these. But humor me anyways and try them out. So let's try, what's another pretty common thing that we've got? Oh, let's do me. Let's do me. I am about 80 kilograms. 80 kilograms. That is my mass. Nice. That's my mass. 80 kilograms. If I wanted to change that into grams, we need a conversion factor, right? And the conversion factor is just written up top here. So we know that, let's see, it's over here. 1,000 grams is equal to 1 kilogram. So put the video on pause here. We know our conversion factor, we know how to cancel things out, and really consciously think about, okay, where do I need to put the kilograms, where do I need to put the grams, and where do the numbers go? So units first, numbers second. Cool, put it on pause, try it out. Nice. So hopefully we figured this one through. Again, if you want to put, so it looks like you've got a distinct top and bottom for both of your fractions, that is a-okay. So put your original number over 1. I might just actually, you know what, let's clean that up a tiny bit more. That's a little bit better there. So let's see, I've got kilograms in the top. I want to cancel out kilograms and end up with grams. So perfect. If I want to cancel kilograms, it's currently on the top. I have to put it on the bottom. Notice how we're focusing on units first. Have to do that. I want to end up with grams. Grams has to go on the top. And then I go back and I think, okay, well, how many grams are in a kilogram? There are 1,000 grams in 1 kilogram and not the other way around. So the 1,000 has to go with the grams and the 1 has to go with the kilograms. Perfect. So then as I go through and as I plug this into my calculator, let's clear that up a little bit. I've canceled the units. That's how I know I'm doing this correctly. And I would put 80 times 1,000. That's 10,000. I keep doing that. 80 times 1,000 is equal to 80,000 grams. Awesome, perfect. Now there's not a correct number of significant digits there. We'll talk about those momentarily. So if you want to try these out, honestly, do what I did. I picked a juice box and I picked me. Pick anything. You can always send me a quick email and ask, say like, I've done these conversions. These are my answers. Did I do them correctly? There's tons of videos on this on the internet. Just look up unit conversions and you will see tons of videos. Some of them might have like pounds and kilograms and stuff like that, but it's always the same idea. Nice. So there's a little bit about unit conversions. I think the next thing that we should probably talk about is just some significant digits, sig digs for short, and scientific notation. Scientific notation. Okay, cool. Sig digs and scientific notation. So in Chem 20, for the most part, we're dealing with multiplication and division, and there's a very particular rule for multiplication and division. There's also a rule for addition and subtraction. We just don't use that very often in chemistry, so we might leave that one out for the time being. And then there's also one for logarithmic functions, which we'll talk about a little bit later on in the acids and bases section. But for multiplication and division, it's really actually easy. So the least number of sig digs in the question, sig digs in question, oh, this is real shorthand, equals number of sig digs in answer. Cool, and that's it. That's all there is to it. So you look for the measurement with the least number of significant digits in your question, and that's how many sig digs you should have in your answer. I may have forgotten something. What is a significant digit? So maybe we'll want to look at that as well. But I'm hoping that people remember that from other courses. I know that you've definitely seen that in Science 10. Maybe we'll just have a tiny review of that as well. So sig digs. Easiest way to look at it for most normal numbers, most of the numbers that we're going to be looking at, it's your first non-zero number, or digit, I guess I should say, digit, and every digit after. Okay, so let's check that out. We'll do a couple examples here and we'll see. So for example, if I had 210 meters, right? And the units, the reason I'm putting a unit here, units are just ridiculously important. Otherwise, you have no idea. If I say 210, you have no idea what I'm talking about. So in this case, I'm going to say 210 meters. 210 meters. So this is 3 significant digits, and I know that because I look at my first non-zero, that's the 2, that one is significant, and then every digit after that. So 3 sig digs. I'm going to abbreviate that even more, SD. If I were to look at another one, let's do 0.001 0.0192. And I look at 0.0192, I'd go through this one, think about how many sig digs? It's my first non-zero, so that's this one, that's the 1, and every digit after. Perfect, so that's also 3 sig digs. Nice, okay, we'll try one more out. Let's do 2.8 times 10 to the negative 3. Let's do moles. And I forgot a liter on that top one, or sorry, a unit. I'm going to put it as liters for the top one. So 2.8 times 10 to the negative 3 moles. Now we've thrown this scientific notation stuff in there, the 10 to the negative 3, which is tricky, right? And it's maybe something that some of us haven't seen for a while, but that's just placeholders. That's telling us how big or small the number. It's not actually telling us much about the number itself besides it's big or small. So really what I look at when I see scientific notation is my first non-zero, so that's the 2, and then everything after, so that's the 8. So this is actually only 2 sig digs. Nice. So that's not too bad. Not too bad at all. Cool. So first non-zero and every digit after. Awesome. Okay, let's check out one last little piece and then we'll start looking at a couple examples, putting everything together. Scientific notation. And when I look at scientific notation, I'm essentially looking at taking numbers that are too big, so have too many digits, and I cannot have the correct number of significant digits because they're just so dang big, or numbers that are so small that they're kind of annoying to deal with and it makes it a little bit easier to write with. So some rules for this: we are allowed 1 digit before the decimal place, then whatever we need after, and the digit has to be a 1 to 9 inclusive, so we can't have a 0, and obviously a 10 is 2 digits, so we can't have 10. So 1 digit before, and then we want to multiply by 10 to the power of x, where x is how many times you move the decimal place, is how many times decimal moved. Cool. So multiply by 10 to the power of x, where x is how many times the decimal moved. We're just going to say one last thing with this. X is positive, so that's x in 10 to the power of x is positive if it's bigger than 1. And by its, I mean the actual number itself, bigger than 1, or negative if smaller than 1. Okay, so let's have a quick look here, just a real quick look at an example or two. So example, put in scientific notation. Okay, so we're going to put these into scientific notation. So I've got 252,619, let's go liters, and I'm only allowed, let's say, 3 sig digs. So I'm only allowed 3 sig digs. So that's a bit of an issue there, right? 252,619 liters, and I'm only allowed 3 sig digs. So I can't just say it's 252, because 252 is not the same as 252,000. It's very, very different. So essentially what we want to do is we want to move the decimal place so that there's only 1 digit. So it's a whole number. The decimal place before, let's work in a bit of a different color here to show our work. The decimal place before was way over here. Right? Whole numbers come after the last digit, and I want to move it from red to where it is in blue. So notice that I've got my 1 non-zero digit in front of the decimal place. That's where I'm moving it, and then I'm moving it 1, 2, 3, 4. Looks like I'm moving it 5 times. So my answer is going to be As I go back, let's get that green felt pen. 2.5. Now I got to make a rounding decision here. It's either going to be 2.52 or 2.53. I have to look at the digit that comes immediately after. It's a 6, so follow regular rounding rules. It's going to be 2.53 times 10 to the power of how many times we moved the decimal place. And remember, we moved it 5 times. So 2.53 times 10 to the power of 5 liters. We've got a positive exponent because it's a big number, much bigger than 1. Cool. So let's try it one more. Let's try with a small number, and then we'll start to look at putting all this stuff together and back to those sig digs. So another example of this. Okay, let's move this up a tiny bit. There we go. Let's do 0.0001983. And we are going to say, put it in a scientific notation, and how many sig digs? Let's do 2 sig digs here, so 2 sig digs. So first off, the decimal is really clear. I'm going to highlight in red. The decimal is right here, so no problem. The decimal is now red. I want to move it so that I have 1 non-zero in front. So I'm going to move it to blue over on that side. So let's see. I need to move it. Let's go back to just our regular green felt pen. I need to move it 1, 2, 3, 4 times to get it from where it started to where it's just got 1 digit in front. So I know that this is going to be times 10 to the negative 4. Oh, I forgot a unit again. Let's do grams. So something times 10 to the negative 4 grams, negative because it's a very small number. Cool. Now I just got to think about what that actual number is. So I'm allowed the 1, I'm allowed the 9, but I have to think, does that 9 round up? So I look at the number that comes immediately after it. It's 1.98. So that 8 is going to actually round that 9 up to a 10, and the 10 is going to go into this place. So it's a little bit messy here. This is actually going to round to 2.0 times 10 to the negative 4 grams. Cool. So that's not too bad. The other thing that you might need to do sometimes is be able to go the other way. So it's more likely that you have to put it into scientific notation, but sometimes you have to go the other way. So maybe check that out and see if you can go the other way. So let's do an example, kind of putting all of these pieces together. So a full-on example. Full-on example. So let's do 256 moles, and let's divide that by, oh, I don't know, let's go 3.52 moles per liter. So again, same thing that we talked about, things on the top we multiply, things on the bottom we divide. So it's 256 divided by 3.52 moles per liter. What else we can do with this? We already talked about how units on the top cancel with units on the bottom. We're doing our conversion factors. So moles is actually going to cancel with moles. What would the only unit that we have left be here? So whatever this works out to be, it's going to be measured in liters. Cool, so let's plug this into the calculator and let's just see what we get. I got 256 divided by 3.5, made a mistake, 3.52. 256 divided by 3.52, looks like we're good to go. So this equals 72.727272. I like numbers like this, 7273, and I imagine to be 72 forever and ever and ever and ever and ever and ever. Cool. 72, that's way too many sig digs that we see in our calculator now. That's way too many sig digs. So we go back to the original question. This one's actually really easy, unintentionally easy. How many sig digs do I have on the top number? Looks like I've got 3 sig digs. How many do I have on the bottom number? 3 sig digs. So what does my answer need to have? 3 sig digs, the least number from the question, from the measurements in the question. So that's just going to be 72.2.7 liters. Cool, that's it. That's really all there is to it. The least number from the question is equal to the number in the answer. Let's do one more example just to really drive this point home. One more example, and then let's move on to something else. A bit of other review in a bit of a different fashion. We're almost done here though. Almost done. So let's do what's another really good one here? Let's use the same kind of units here, just for simplicity's sake on my mind. Let's do 210 moles divided by 0.0042 moles per liter. Cool. So we see moles cancel with moles, same way, units on the top cancel with units on the bottom. Whatever the units are going to end up, it's going to give us liters. Let's get out the old calculator here, clear that up, and let's do 210 divided by 0.0042. 210 divided by 0.0042. That gives me, holy mackerel, I'm not even planning this, it's just giving me a real nice number, 50,000 liters. Now let's look at how many sig digs, before we write out our answer, let's look at how many sig digs. So on the top measurement, I've got, let's see, 3 sig digs, and on the bottom measurement, I've only got 2 sig digs. So the rule is, the least number from the question should be equal to the number in my answer. So I'm allowed 2 sig digs. So 50,000. Well, I can't just change that to 50 because 50 is not the same thing as 50,000. So I'd have to put this into scientific notation. So I think it's going to be 5.0 times 10 to the power of. Every time I touch the smartboard, that goes away. How many times do I move the decimal place here? So I move it 1, 2, 3, 4 times, and I just counted on the calculator there, times 10 to the power of 4 liters. That would be my final answer. Perfect. So we put everything together. We are going to keep going with this. So let's see. You might want to look at the time. It looks like we're at 32 minutes. This is going to be a bit of a longer lesson. You could put it on pause. You could actually, you know what we'll do? I think I know what we'll do. We'll just stop this recording right here, and then we'll have another one, so it'll be a shorter review one. So I guess I said 2 lessons. It'll kind of be 3 lessons as we look at it. So I'm going to pause this one or stop this one here. So if you want to take a break, you want to find some more practice to do with this, just look up practice about sig digs and stuff on the internet, watch a video or whatever. But it's getting kind of long, so we'll stop it here. I'll have another review one, and then we'll have our actual chem material that we need to look at. Okay, so talk to you again soon. Bye for now.